Hello guys, welcome back to Rahman Chemistry Coaching Academy. I am Dr. Taj Rahman and this is our ninth lecture on stereochemistry. So far in our previous lectures on stereochemistry, we discussed that isomers are the compounds that contain same atoms bonded together in different way. If the connectivity of atoms in the two isomers is different, they are called structural or constitutional isomers. And if the connectivity of atoms in the two isomers is same but in different three-dimensional arrangement, then they are called stereoisomers, and this phenomenon is called stereoisomerism. Stereoisomerism is further classified into two types, that is conformational isomerism and configurational isomerism. Configurational isomerism is further subdivided into geometrical isomerism and optical isomerism. We will discuss them one by one in detail. Let's get started with the conformational isomerism. Guys, in our today lecture on conformational isomerism, we will try to learn about conformational isomerism and the various terminologies used in conformational isomerism, that is torsional strain, angle strain, and steric strain or van der Waals repulsion. We will also explain how different conformers or rotamers are formed and how they can be represented by using Saha structures and Newman projections. We will also try to learn about conformational analysis of ethane. Now consider this is an ethane molecule with molecular formula C2, it's 6. Both carbon atoms in ethane molecule are sp3 hybridized with bond angle of 109.5 degree. There is free rotation around carbon-carbon single bond in this ethane molecule, and due to this free rotation, different arrangements of atoms are possible in this ethane molecule. These different arrangements of atoms caused by rotation around a single bond are called conformations, and a specific structure is called conformer or conformational isomer or simply rotamers. These conformers are not isolable as they have low torsional strain or torsional energy and are easily interconvertible to each other. However, there are some isomers, conformers that can be isolated by anyone with distinct energy more than 80 to 100 kilojoules per mole. These isolable isomers are called atrope isomers. The example of these atrope isomers are series of bivinyl compounds. Now look at this ethene and ethane molecules with molecular formula C2H4 and C2H2. Both the carbon atoms in ethene molecule are sp2 hybridized, while in ethane are sp hybridized. The conformational isomerism is not possible in these molecules as they both contain double bond and triple bonds between carbon-carbon atoms. That they have restricted rotation due to the presence of pi bonds, and hence the bond will break if sufficient energy is provided to the molecules to rotate. This is the staggered conformation of ethane, and this one is the eclipse conformation of ethane. In staggered conformation of ethane, the carbon hydrogen bonds on both carbons are far apart from one another, while in eclipse conformation of ethane, the carbon hydrogen bonds on both carbons are parallel to each other. Conformational isomers are conveniently represented by two ways, that is, Sahar's structures and Newman projections. These are the Saha structures and these are the Newman projections of ethane molecule. These representations view the carbon-carbon bond from an oblique angle and indicate the spatial orientation by showing all the carbon hydrogen bonds. These representation view the carbon-carbon bond directly end on and represent the two carbon atoms by a circle and a dot. The front carbon is represented by a dot and the substituents on the front carbon are represented by lines going to the center of the circle. Similarly, the rear carbon or back carbon is represented by a circle and the substituent on the rear carbon or back carbon are represented by lines going to the edge of the circle. In ethane, two extreme conformations are possible, that is staggered and eclipsed. In ethane, the lowest energy most stable conformation is the one in which all the six carbon hydrogen bonds are as possible from one another. This is called the staggered conformation of ethane. Similarly, the highest energy least stable conformation of ethane is the one in which all the six carbon hydrogen are as close as possible. This is called eclipse conformation of ethane. In between the eclipsed and staggered conformation of ethane, there are infinite numbers of conformation possible. The staggered conformation is about 12.1 kilojoule per mole lower in energy than the eclipse conformer. These are called skew conformations. Thus, the staggered conformer is more stable than the eclipse conformer. One thing should be noted that conformers have different physical and up to some extent chemical properties. Now look at to this eclipse conformer of ethane which is unstable and have higher energy about 12.1 kilojoule per mole than the staggered conformation of the ethane. The rotation around carbon-carbon single bond by providing 12.1 kilojoule per mole of energy caused the staggered conformation to convert to eclipse conformation in ethane molecule. Thus, this 12.1 kilojoule per mole of energy which caused to rotate one part of the ethane molecule with respect to the other part of the ethane molecule is called torsional strain or torsional energy, where the torsional energy or torsional strain can be defined as the destabilization that results when adjacent atoms are not staggered. Again, see this eclipse conformation of ethane in which all the carbon hydrogen on the front carbon and back carbon atoms are parallel. Due to this proximity and parallel natures, these all carbon hydrogen on both carbon atoms, that is front and rear carbon, repel each other, and this repulsion is called steric repulsion or van der Waal repulsion, where steric strain or van der Waal repulsion strain is defined as the destabilization that results when atoms or groups or non-adjacent atoms are too close to one another. During conformational interconversion from eclipse to staggered form of ethane, an angle change can be observed between the carbon-hydrogen bond of the front and rear carbon. This change in angle is known as angle strain, where the angle strain is defined as the destabilization that results from distortions of the bond angles from their normal value. Any angle between the carbon-hydrogen bond of the front carbon and the carbon-hydrogen bond of the rear carbon is known as dihedral angle, which goes full circle from 0 to 360 degree. These are the ball and stick models of the staggered and eclipsed conformations of ethane. These four are side views and these two are the end-on views of the staggered and eclipsed conformation of ethane molecule. This is again the space-filled model of the eclipsed and staggered conformation of the ethane molecule. In this eclipse conformation of ethane, the carbon-hydrogen bonds on the front and rear carbons are parallel and close to one another and cause steric strain or van der Waals repulsion. Where in this staggered conformation of ethane molecule, the carbon-hydrogen bonds on the front and rear carbons are further apart from each other and thus there is low steric strain or van der Waals repulsion. Now we are going to explain conformational analysis of ethane. Conformational analysis can be defined as the study of the energy changes that occur during the rotation of one part of the molecule with respect to the other part through single carbon-carbon atom is called conformational analysis. Now look at to these Sahar structures and Newman projections of the ethane molecule. In eclipse form, all the carbon-hydrogen bonds on both the front and rear carbons are parallel and close to each other and thus repel each other. Here we can say that steric strain is maximum. Now we are going to rotate the carbon-hydrogen bond on the front carbon with respect to the carbon-hydrogen bond on the rear carbon of this eclipsed conformation at an angle of 60 degree. We get this structure. This is called the staggered conformation of ethane, in which all the carbon hydrogen bonds are part apart from each other and thus due to this the steric strain is minimum here in this staggered conformation. Now if we rotate further this carbon hydrogen bond on the front carbon with respect to the carbon hydrogen bond on the rear carbon at an angle of 60 degree, we get this eclipse conformation of ethane. So this means that by each 60-degree rotation around the full circle goes from 0 to 360 degree, we observe these three eclipse conformation and these three staggered conformation of ethane is shown in this diagram, a graph of potential energy versus bond rotation in ethane molecule. The difference in energy between two conformers of ethane molecule is called torsional energy or torsional barrier or torsional strain. This is the eclipsed conformer with an energy of 12.1 kilojoule per mole, and if this eclipse conformation is converted into this staggered conformation, it will release this 12.1 kilojoule per mole of energy. Again, if this staggered conformation is converted into eclipse conformation, it will required this 12.1 kilojoule per mole of energy. So this was all about conformations and conformational analysis of ethane. Thank you for watching my video lecture. If you find this video interesting and informative, then please like, share, comment and subscribe my channel for more videos.